us for another hour or two to follow. I want to tell you a bit more about the Embedded Systems group. So this group has started, I think, about a year ago. And since we started, we are meeting almost nearly every month to have presentations and talks to teach everyone about hardware and hardware engineering. So hardware engineering is something that has become very, I would say, sorry. So hardware engineering has become something that's very accessible these days. So you can buy very cheap microcontroller boards, you can even buy FPGAs. There is a wealth of information of different systems. So it is really something that everyone can do nowadays, independent of if you have a very strong, let's say, science-y or software engineering background, or you're just starting off. And even, we will show you even today how these things can be programmed in Python. So even Python is a possibility now to program hardware systems, and that also makes it in some way more inclusive. So we are trying to address different topics related to hardware. So some of these topics are the software engineering side. How do we program these hardware systems? What are the languages we are going to use? What are the actual design patterns, and what are the kind of tools that we need? But we're also interested in the hardware and electronic side of things. You know, how does a computer actually work? I mean, what is inside of a chip? And how do we take, you know, have the best, when we take all the features of a chip and make the most of it? So this also involves things like, you know, designing actual electronic system, PCB design, which we haven't done very much. Hardware security is an issue. So we try also to talk a bit about hardware security at some point. And overall, the scope of the group is quite large. So we don't want to limit it to just one side of it. But since the communities which exist already are very software-centric, the Embedded Systems group tries to complement this a bit and have a more hardware-centric community that, you know, caters for these needs as well. So we're meeting, as I said, every month. We have our Meetup website. We have also a WhatsApp channel, which you can join. And I will send later a slide around just to make you aware of that. We have a GitLab page as well. And we're trying to build, you know, a growing community of engineers who like to learn about hardware, who like to engage in projects. And that's basically what we are. And today our topic is about the Raspberry Pico. So the Pico is a fairly, I wouldn't say, it's still fairly recent comparing to the Pi, the Raspberry Pi, which a lot of people know. And we will tell you a lot of kind of interesting features and aspects of that chip today. So David Barnett is going to give the first talk today, and he's going to tell us everything that you always want to know about the Pico, but maybe you were afraid to ask. But you can always ask us as well if you want to. Thanks, David.
Thanks, Frank. Okay, hi everyone. David. Do you want to talk to me about the Raspberry Pico? There's a little about me. I'm a software engineer.
Yes.
Getting right. One moment. Okay. I'm a software engineer and tinkerer. I worked as a software engineer for 11 years, most recently at the Big G, and some other startups, kind of earlier in my career. Had some little embedded systems experience working in smart lighting, accessibility projects, and I still have an interest in home automation. So just a smattering of different interests. Okay, so the Raspberry Pi is a brand. The brand is about being an engine for creativity, learning, and innovation. There's a real emphasis on having very accessible, low-cost products and having them be very friendly for hobbyists and education, to be able to get a lot out of very cheap, easy to obtain hardware. The Raspberry Pi has been around for a while. This talk is about the Raspberry Pi Pico, which is a little bit different. So the Pico is a very small microcontroller system that was released in January 2021. It retailed about $4. It is, in comparison to the Raspberry Pi, the Raspberry Pi is a full-blown mini computer. It can run Linux. It has, you can watch it boot up, run terminals, OS, all that. It does have, in addition to being a mini computer, has a lot of ports for being able to hook up to interesting things. The Pico, in contrast, is much, much smaller, more constrained system, very inexpensive, and it is based on the RP2040 chip that we'll talk a little bit about. So here I have kind of, around the 1970s, when you were doing embedded systems, you were not working in software, you were connecting up components, transistors, and wires. And then it became a little bit easier to have creativity, as a hobbyist when were programmable systems. Then we got the microcontrollers, the Arduinos. This here is the Raspberry Pi. I forget which model, but this is a full-blown computer. And then in 2021, they released the Pico, which is this card and the RP2040, this little chip in the middle. So there's a regular edition and a W edition that also supports Wi-Fi and Bluetooth on the chip. Okay. By the way, anyone has questions, feel free to raise your hand. We're going to move kind of fast through some of it, try to balance out the time, and maybe leave plenty of time at the end for questions if we can. All right. So you might be wondering, why would you get this particular device instead of some other hardware? This hardware actually combines, even though it's very resource constrained, it combines a lot of really interesting features. It's not as fast as some other systems you may or may not have heard of, like ESP32, that runs at about twice the clock speed. But it has a lot of things, programmable I/O, direct memory access, and different features where you can really get some very interesting things out of it if you get down into the mechanics. You can program in C assembly if you want. There's a system called MicroPython and CircuitPython where you can kind of set up the device to run Python scripts that makes it very easy to get started quickly. And the datasheet is very high quality, great SDK. I also found a lot of the official examples they have are very useful for figuring out how to do different things. But it is resource constrained. You might say in some ways that it is slow, but we'll see a demo later, hopefully, of VGA video signal processing, where you can really see how these different features combine together to get some really impressive performance. Oh, thanks. Okay, so what kind of things can you do with it? There's a surprising amount you can do with it compared to its size. Some like projects that people tend to do hook them up to motion sensors, like weather, temperature monitors, signal processing for audio and video. The VGA, we'll see later as an example of that. There have been some people who somehow have ported different Nintendo games to run on the Raspberry Pi using some really impressive tricks. Home automation, you're usually going to have wireless, the wireless variants used for that, but all kinds of Internet of Things. And then this, I thought was kind of neat. Somebody made a magic mirror, a little display behind their mirror using it. Okay, here's a big diagram. Before I get into this, any burning questions so far? Anyone? Okay. So there's a lot here, and I'm not going to like point through all of it, but I just kind of have it all here so you can kind of get oriented around how the architecture looks. A few things to notice here, if you can see it. Well, I don't know if you can, but there are two processors here that are kind of connected up in this configuration. There's you'll see here memory, and that's connected to access the flash storage through this QSPI interface. And then USB is very important to unlock some interesting things. And over here, you'll see a lot of GPIO pins. That's general purpose IO. So that's one of the Pi's like very popular features is it has, you can just hook it up in a lot of ways to a lot of different things. So all the input output is going to go through this bank here, and then has a lot of systems here, peripherals, that can control what and how what it's going to do with those connections and how it's going to work for different protocols and things like that. So that's the lay of the land here. And this is the chip here, the RP2040. Here, I won't say too much more, but this is the processor named ARM Cortex M0 Plus. There are two of them, and 30 GPIO pins, which is a lot. And we'll talk about some of these features, DMA and PIO later. And lots of peripheral systems, yeah, 8 PIO state machines. And you may or may not have heard of these different kind of communication protocols, I2C, SPI. It supports a lot of them and has ways to add support for protocols that you've never heard of. So that's the chip, the RP2040. Here's how it looks on the Pico board. There's really not a lot there on the board. There's a whole bunch of connections, a crystal, flash memory, and this I looked up as a regulator, a voltage regulator. So that's it. So a lot of the magic is just right here in the middle of the board. And there are also much smaller RP2040 boards that are basically just the size of the chip.
Question, what is a crystal?
What's the what?
What's a crystal? Crystal, what is that? Because I don't know about electronic branch.
Oh, the crystal, yes. So, here. So, for processors to go through executing instructions, they need some kind of time basis, some way to count the passage of time. And so a really important part of how it works is connecting the I/O for the crystal signal to a crystal oscillator that helps it generate a stable timing signal. So that's not on the chip but there's not much else that's not. Okay, so this part is fairly bread and butter. Not gonna blow anyone's mind, but just to kind of set the scene for things it can do. Here's how a hello world implementation in C looks. So you can take this, build it into a file that you can drop onto over the USB bootloader onto the Pico, and then have it run, and then it will spit out hello world every second on this USB serial interface. So it's very easy to use without connecting up a bunch of other hardware. You just plug it in, put it in boot mode or in flash mode, drop the code onto it, restart it, and connect up to it, and you're getting the output. And then another very simple example, there's on most boards there's an LED that's just the default LED, and here's what the code looks like in C for driving that LED, putting it in output mode, turning it on, waiting, off, waiting, and looping around. And if you are programming it and having trouble getting it to work, it's got a really handy debug interface on the bottom, serial wire debug. And there's a few different ways to connect up to it, but one of the popular ways is just getting another Pico, because they're $4.80 pesos. And you can program this second Pico to be a probe driver for the first one and step through. Okay, so that's the very basics. Most embedded systems are going to have those kinds of features, but there's more. So I mentioned here there's peripherals, input output, and the USB is a pretty handy peripheral as well. So there's lots of things you can hook it up to, and lots of configurations for how you can drive it to work. As an example, beyond just making an LED blink, you can hook up to these cheap little LCDs. Usually they're going to work over SPI or I2C, I think sometimes UART. But one of those protocols, you just hook it up to the right pins, program it the right way, and you can spit out text that you want to go on the LCD. There's a analog to digital converter on there. Most embedded systems microcontrollers are going to have something like that. This actually is kind of interesting. Has 4 inputs to take a voltage level, read it, and spit out a ratio of how high or low that is. That's what the analog to digital converter does. And a 5th kind of virtual one that is hooked up to kind of a temperature sensor on the chip. So it's not a very good temperature sensor if you're wanting to get a very accurate read, but you can just get a Pico, hook it up in a very simple way to read something corresponding to temperature and spit it out. So super easy without any other hardware. And then hooking it up to lots of other things. There are lots of, they call them hats, hardware. I don't know, they're hats. And so you can just plug in the boards, the Pico boards, and add lots of little ports, extra circuit components, and just really expand the capabilities. SD card slot on this one. And you can also get lots of cases to make it look prettier and make it a little more rugged. Okay, now we're going to get a little fancier. So the Pico has not one but two processors, two cores. When you look at the code examples, you'll see it'll start up, run code instructions on processor 0, and have processor 1 in deep sleep mode. But the SDK has a multi-core launch core 1 thing that you pass kind of a function handle, and it will start running code on processor 2. They can perform tasks independently. They have some very intricate systems for coordinating between each other, synchronizing, and not stomping on each other as they're both doing work at the same time. Here is kind of zoomed in. You have core 1, core 2. Some of the interesting things, they have a FIFO buffer, first in, first out, from 0 to 1, from 1 to 0. And then they have some locks to help if they're accessing the same resources, where they can both wait and make sure CPU 1 doesn't access it until CPU 0 is done. The interrupts are also very useful for timing and synchronizing. And they have this thing, the single cycle IO. This whole block is the single cycle IO. It's got a lot of kind of very tight timing things that run each on one processor cycle. It communicates faster than a lot of the more general purpose IO, so that it's not holding up the processors. And then they have, here's core 0, core 1. They have this AHB Lite advanced high performance bus Lite to connect in a coordinated way to the RAM, the flash, all the other systems. And then this advanced peripheral bus goes out, is not as tight on the timing, but goes out to a lot of other parts of the hardware. Okay, so that's the CPU, the processors. There's another system called the PIO, Programmable I/O, that helps with a particular type of I/O problem. So you've got this system, you can run code, you can use it to drive outputs to have a wire go high and low. You can drive inputs, but if you've got the CPU instructions driving each change to the I/O, there are going to be some disadvantages. Does anyone know what they might be?
Might not be very fast, so you have to produce very high accuracy signals, low latency signals.
Yep. Speed, timing. You're also going to be eating up time that the processor can be doing something else, having it continuously go and drive signals high and low or whatever you're doing. And just, it's generally going to be high complexity. So does anyone happen to know what you call that when the processor is just driving signals up, down, instead of sending a higher level signal? It's called bit banging, and it can be okay in small systems, but it has disadvantages. So instead of bit bang, the programmable I/O has has tiny coprocessors. They can be programmed in a special microassembly language as their own system, and they can be used to power lots of arbitrary high-level output input patterns. You can, in fact, implement most of the protocols that the device supports manually on the programmable I/O instead of using the built-in support for I2C, SPI, and all that. Or you can invent your own protocols. You can use it to drive video signals. So here's kind of how it looks. As 4 state machines, you set those up with a set of instructions. They look like assembly language, because they are. And they have input and output buffers to handle data. And then you can map those to those 30 GPIO pins to tell them, for instance, set up to go in a loop and turn pin 0 high, wait a second, turn it off, wait a second, and then just have that entirely offloaded from the main processor. Here is some of the how the buffers look. If you're curious, I'll just move through that. So here's the assembly language. It has 4, 5, 6, 7, 8, 9 instructions: jump, wait, in, out, push, pull, and a lot of those have special slots for indexes and things to chain those instructions to other kind of high-level operations. So you don't have to memorize these, obviously, but just to get the gist of the assembly language it uses. And then what you can do is just write out in that high-level assembly, or that assembly language, you'll have a separate file. You'll kind of crunch that into a header file that just gets you a bunch of numbers, and then load that into the instruction memory for one of those PIO units. So the processor can drive what the PIO is doing. So that lets us avoid bit banging. Instead, we're doing something akin to word banging, where we're setting it up to take blocks of data and do something with it in a structured way. And you can produce complex signals or receive complex signals without tying up any CPU resources. Older systems wouldn't have quite so fancy of a way of doing that, but they would have kind of specialized chips. Usually they would need to do very special kinds of input-output signal processing. So they would generally have something like that. And that helps to make up for the relatively lower clock speed of the Pico. And then DMA, direct memory access, is another feature that is really powerful, helps to like really unlock some really cool use cases. So at a high level, it's just kind of a way of orchestrating how memory moves around. But it's very kind of scriptable almost. So you can chain operations in really interesting ways. There's even something for doing checksumming on the data as it's coming through. So all kinds of really high-level capabilities in how it's set up. But generally, it's going to be, as an example, you can set it up to periodically copy data from one place to another. And Frank will have a lot more to show on that. Okay. How are we on time? All right. So that's the end of the main talk. If there are any questions, you can talk now. Or Frank is going to also give a demo. We can have questions after the demo, possibly.
Do we have the second microphone?
Yes, it's over here.
So thanks, David. It's very interesting. It's a very nice introduction of the features. So you can already see that this chip has a lot of different features and that need to be understood and studied in some way. So we had one question. I think someone asked, I think in the online chat, what the boot cell button is used for on the board.
Let's go way up here. Okay. Actually, I think Frank would do a better job explaining that than I would. There are usually two buttons. There's a reset button. It may do more than one thing, but the main thing that I think you use it for is if you hold that button down while powering on, plugging in the device, then it, instead of booting up in the normal mode where it runs whatever has been programmed onto it, it loads into the programming mode where you can write code onto it. So you'll hold that down, plug in the USB, and then it'll wake up ready to receive instructions.
So it's basically for loading code onto the chip, onto the board. So most boards have a certain thing called a bootloader, and the board will expose itself on the USB as a device, as a block device that receives data. So it's just to tell it where when you reset it, you press the button, and then the USB port will suddenly present itself as a character block device, and you can send data to it. So that's how you program it, basically.
Yeah.
You reset it pressing that button, and I'll show you that maybe in the next part of the talk. There was another question about the GPIOs, and I think it's related to the voltage level. So there's different standards of voltage. And the two common ones are 3.3 volts and 5 volts. And I think the question was, how many volts can you support? What standards do you support on these GPIOs?
Oh, I'm not sure. I think they generally run at 3.3 volts.
Yeah, I think so as well.
They're plugged in on USB, and there's a regulator, but there's also a power input somewhere in there. And I'm not actually sure if you can directly drive 5 volts if you power it with 5 volts, or how that works offhand.
Yeah, I'm not 100% sure myself, but I think it's probably just one standard that you can use for the board. So yeah.
And also, I have some a Pico here that I can pass around. I forgot to pass it around earlier. And this is if you can even see it, is a RP2040 board that's basically just the size of the chip and has some stuff on the back.
So very small.
Yes, has about the same capabilities.
Cool. Any more questions from you guys? What's your feeling?
What kind of projects?
Thank you. With what kind of projects you can start to use the Raspberry Pico?
What
would you recommend?
To recommend? Yeah. I mean, it's very inexpensive to just like buy one and play with it. It's made for learning, so Hello World is a great place to start. If you're familiar with what it can do, I think you'll tend to, depending on your interests and lifestyle, you'll tend to run into little things where you need to hook something up to something else, and you'll say, oh, I can just put a Pico there and do that. So you'll kind of discover needs as you come to them. And obviously there are things like Magic Mirror where you can sit down and say, hey, I want to do something cool, what should I do? And work at it more from that end. But it's really kind of versatile, and like I think once you're it's great for learning, and once you're familiar with it, then you kind of have more organic, interesting cases you can think of where you can plug into it. I personally, with the wireless edition, have some plans in mind to try to hook up some home automation science fair projects.
Awesome. Thanks so much.
Quick question. The green one is the Pico, right? The Raspberry Pico.
Yes.
What is the blue?
That is this blue one. It's the same chip, the same RP2040 chip
This one, right?
in the middle. Yes, and most of the same components. It's just a much smaller form factor. So
Okay, right.
it's the it's called the Zero RP2040 Zero.
So, great. Are there any more questions for the Pico?
Yeah, actually, I have a question. In my personal case, I don't have experience with electronic components. There is some way to start to use this hardware without take care about electronic, maybe to some personal project using the Wi-Fi or something like that. And also, I have experience with high-level programming language. It's possible to use, I don't know, Java or JavaScript or something like that to program in there.
Okay, that's two great questions. No, I'll answer the second one first about what languages can you use to program this. Generally, people will use C, sometimes MicroPython, CircuitPython, and I guess sometimes C++. You can also use Rust if you're into that kind of thing like I am. But it's kind of overkill using very high level languages for embedded systems. And in fact, the further you get from the hardware, the kind of harder it is to map back onto the mental model of the specialized hardware. So when you add layers of libraries and things like that, even in C, sometimes you'll find, oh, the SDK doesn't support something that I need to do it in C. I'll need to like build my own library to kind of add that feature. And if you're working, I have not seen anyone using JavaScript or Java. I mean, on the Raspberry Pi, I'm sure you can run those fine. On the Pico, it may be more challenge than benefit.
Probably on Python is okay.
Yes, so the Python is very common to use. You'll load a kind of a core system that will be able to execute Python, a variant of Python, and then give it instructions in Python text code. And then you were asking on the hardware side, what kind of things can you do without buying a lot of extras, having extra stuff to hook up to it. I think I haven't gotten very far with using it honestly in a lot of different applications yet, but I would imagine if you don't want to deal with soldering, making electrical connections, like buying LEDs and things to plug in, you could probably do a lot with a Pico W using Bluetooth and Wi-Fi, where you just have the brain and wireless, and then if you want to hook it up to like some little peripheral and hook that up to wireless, then kind of being able to hook up to a wireless network would do a lot of the like lighting up the magic for you.
most of the time you're just connecting the device with a few wires. There's a few things you need to be careful about. For instance, if you have I2C, you might need additional resistors, pull-ups. But I mean, as long as you're matching the voltage level and you're careful with the consumption of power, so if you have a consumer which draws a lot of power, usually these boards cannot handle a lot of current flow. So that's one of the things to be careful about. But I think in terms of hooking up devices, I mean, Arduino has even a standard for that. So they have like this kind of fixed interface. And I think with the Pico, I'm not 100% sure, but I think you might have similar things there as well. So, but usually the hooking up is not such a big issue. And there's also a lot of information on the web that we say, yeah, connect this kind of display to it. This is how you do it. And then you just need the right software on the system that uses the internal periphery. What I'm going to show next is a bit more complicated because there's nothing in the chip that actually allows you to do that. And just to answer the question, it's a really interesting question. So why is Java not being used? So I used to work on a research project which was trying to build a safety critical version of Java that actually can run on embedded systems. And it was based on real-time Java, which was the Java subset, and actually the first Java community request that was ever produced, JSR1. And there were some virtual machines specifically that run this Java version. And it was limited in terms of what you can do with memory. Because an issue, of course, you have in Java is garbage collection. The concurrency model in Java is maybe sometimes not what you want in real-time systems. So you need to kind of have a more disciplined way to deal with memory and things like that. And I haven't followed it very much since I left the project in academia. And I think there are some efforts to use Java in the safety critical industries, but I would still say that Java is probably not very prevalent there. So C and C++ is what still is used a lot because you have the proximity to the hardware. And I mean, C has a lot of issues as well in terms of undefinedness, in terms of writing safe and secure code. So that's where Rust comes in. I think a lot of movement is now towards Rust because it gives you a priori safety of certain things which otherwise could be problematic. And one reason to use C is really to use the PIOS, because in Python you can use the Python interface, but you are not able to take full advantage of all the features. And when you write, for instance, interrupt request handlers, they are usually small bits of code that need to run very fast because they're interrupting the rest of the system. They're just, something comes in, you have to react. And that is where you really profit from C because you can, break this down to just a few lines of assembly code sometimes. And so there's no way around sometimes in embedded systems to go to the lower level languages, even sometimes to assembly. But depending on what you want to do, if I have a system that needs to react within 5 minutes or maybe even 1 second, you don't need the low latency responses. You can do it in Python. And I think it's still good to open this engineering to a lot of people who are maybe not so familiar with C. As universities nowadays, I think they will not. We didn't learn C at university. We started with Java and functional programming. And I think that's unless you really study embedded systems, is maybe where you often start nowadays. So just to answer the question.
Yeah.
Are there any more questions about the Pico or some general?
Thank you. I have another question. Maybe you have already mentioned that, but I just want to be sure. Does the Raspberry Pico support also wireless protocol communications?
Oh, wireless, yes. I didn't talk very much about it because there's so much ground to cover in so little time, but
yeah, because I saw that you
yes.
can substitute the ESP13 too.
Yeah. There's, I think, a higher and less, more expensive system is the ESP32 that is in some ways comparable. The Pico comes in like Pico and Pico W editions, and the Pico W, I didn't say any more than this about it, but it has built-in support for Wi-Fi and Bluetooth. So if you want wireless, get that, you're good to go.
Awesome. Thank you.
And you should stay for the raffle.
Yeah.
So yeah, it's and the nice thing is the chip is very cheap, and it's mass produced, and it's I think probably one of the cheapest chips you can buy with these features. Cool. Any more questions maybe from that side? Otherwise, I would say first, thanks very much, David. It was great, and learned a lot about the Pico and the features. We will have a short break now of maybe 15 minutes. So we're gonna meet again in 15 minutes, and then Zonatech are gonna give us a little bit of some exciting things that are going on with the company and opportunities. And then we will have another talk, and yeah, about going more into the details, how we use the Pico, how we use the state machines, and so on. So yeah, hope to see you in 15 minutes. Thanks.
There's pizza and drinks over here.
And
so
we have pizza here and drinks, so help yourself.
there's lots.
Beer's not going to be served after 9, so if you want to have a beer, you should be quick and have one. And yeah.
Thank you. Yes, he mentioned soda, and also you can
We live? Okay, everyone, thanks so much for staying. And our sponsor, SolarTech, is going to tell you a bit more how amazing SolarTech is as a company. Go ahead, please.
Thank you. Well, thank you all for being here. Thank you for your time. I am Andrea Martinez, and I work as a recruiter at Sulatec. So I want to talk about us. I want to talk about what we do, about our culture. If you have any questions, any doubts about the company, please let me know. Okay? Great. So, well, let me change. Well, to start, I would like to mention what is the meaning of Sula. And Sula is our interpretation of Hebrew slang for a place that once you found, one will never want to live. And I want to talk about what we do. Well, Solatech is a company that is based on USA, and we have operations in Turkey, in Ukraine, Poland, and Romania. And also we expanded to Latin America. And for now, we have operations in Mexico, Argentina, Brazil, and Colombia. We are growing here in Latin America. We are looking for growth more here in Mexico. So, well, what we do? We are, well, we are focused on development oriented. Sulatech is a company who have multiple clients, almost all from the USA. And the projects that we seek are development oriented to support our clients. The projects that you can find with us can be for front end, back end, full stack, QAs, business analyst, application support, etc. You can find a lot of type of profiles with Sula. So I'm going to move again. Talking about our culture, I would like to mention that at Solatech, we care about people. We care about people, talking about professional growth and also personal growth. Talking about professional growth, I'm talking about the last year in 2023, 50 engineers that work with us grow as, well, the seniority level. So you can find here opportunities to grow professionally and also personal growth. For this, we have these Sola Talks. And in these Sola Talks, you can talk about any topic that it's for your interest. It can be a professional topic or also personal interested. So I don't know, if you want to talk about your hobby and your hobby is, I don't know, doing exercise, you can propose to talk about exercise or anything. So we like to learn about you, we like to listen you, and also, Solatech don't care only about the people that are working at the company. Solatech care about this social impact. We are really, really interested in having this social impact, and we focus on charity. So one of the initiatives that we have here is that if you want to do a donation, Solatech match the donation that you do for any charity. And also we run twice a week for a cause. So the important here is doing things for people that are not in the company and who is needed these donations. So I think it's very important for us, the people that are working with us, and also all the people that are out of the company. Also, we are very interested in providing transparency, and the communication in Solatech, it's very fluid. we don't like this pyramid scheme. So if you want to have a conversation with the CEO, you can contact him directly. You don't have to, I'm going to talk about first with this person and then with this person to can talk. No. You can speak or take a conversation wherever you want. And well, as I mentioned, we don't have this pyramid scheme, so you can take a conversation to everyone. If you need any help, you can ask, and if I can help you, I'm going to help you. If Juan can help you, Juan is going to help you. You always are going to receive the help that you are looking for. So for now, I'm going to show you a video. Thank you. I'm going to show you a video about the Latin America culture, so you can see, not only listen to me about our culture. Oh, well, thank you, but
Welcome to Zulatech Latin America, where passion and excellence thrive in a people-first culture. Let's discover what it's like to work with us. We're committed to delivering high-quality solutions and embracing challenges with clarity, and our culture is driven by our core values: extreme ownership, speak up, and learn from failure. We believe in fostering the well-rounded growth of our team members through our fundamentals: sports, charity, and a commitment to living a healthy life. By embracing these values, we cultivate a balanced and fulfilling work environment, and yes, even on distance. And as we embrace our multicultural community, we keep growing. This is Zulatech Latin America. Join us.
okay, well, here you can see some things that we do as a team. And for now, I want to know if you guys have any questions, any doubts, if you want to know something about us, culture, or any other things. No?
What relates to hardware as well? Hardware engineering, does Zulatech also work on hardware engineering, or are they mostly focused on software?
Well, the projects that we have is focused on developing software, but we have any others opportunities to grow, not only as an engineer. Actually, now we have open positions for UX designers, so there are not only opportunities to grow as an engineer. We look also this type of profiles, but we are more focused on developing software.
But I like very much you emphasizing work-life balance, because we all struggle with that.
Yeah.
And I mean, it just comes with the job. And sometimes computer scientists, you need to remind them to stop working.
Yeah, definitely.
And, yeah.
Thank you.
We have a question from the chat.
Yes.
It says, what industries is Zulatech mostly involved in? What industries?
Well, we focus most on the e-commerce industries. One of our clients, I'm going to mention the most famous, as I can say, it's Pandora, Nordstrom, Reddit also is our client. So you can find different types or industries here, but most of them are focused on e-commerce. Any other question? No? Okay. So, well, and now I only want to invite you to visit our websites. No. Yeah. Join us online. You can visit our website, or you can also follow us on social media. You can find us like a Zulatech in all the platforms. And if you want to see more about our culture, I invite you to visit our YouTube channel. There you can find more videos about the different cultures that we have, talking about Europe. So as I mentioned, we have operations there. So there you can find also some comments for engineers that are working with us, actually, speaking about us. So if you don't have any other questions or doubts, please join the event. If you have any other questions or doubts after the event, you can ask for anyone of Sulatech company, and we can answer all your questions, okay? Thank you. Your turn.
Thanks very much, Andy, and very, very nice introduction to the company. I'm
Thank
sure a
you.
lot of our listeners also on YouTube appreciate that. So I'm just quickly gonna unplug and plug in my machine so that you can see the screen.
He's gonna.
And I just move this a bit, maybe. It's just we need a longer cable. Right. Just put this one here. Yeah, I think that looks good. Let's hope that works. Just, yeah, okay. Fantastic. So thanks for everyone online who's still here. And thanks to everyone. Just 1 second. Let me see if that works. Otherwise, just have to do it by hand. Yeah, it does seem to work. Great, and thanks for everyone who's coming today to the social. The community is you, basically. So we're trying, of course, always to advertise our meetings and have more people coming along and putting up kind of a variety of diverse talks. And yeah, for me, it always makes me happy if we get, more people to come along. So if you think it was useful, if you enjoy it, and you want to see more of that, so tell your friends or colleagues, and we will keep the group running. And if you like to give a talk as well, so see, everyone is invited to give a talk. We don't have a kind of list of like priorities and things. So just let me know, and we can surely accommodate that. And just tell us what you'd like to talk about. So we don't always have a topic. Some of our socials are just giving talks. So David gave a very nice introduction what the Pico is about. And something that you would have maybe gathered from the talk is that the Pico has a lot of different features, and these features can be used in different ways. So what I'm going to show you is now how all of this comes together if we want to use the Pico to generate a VGA video signal. So let's start, and I'll just, this is just a bit about myself. So I'm not actually a hardware engineer, so sorry if you thought that, but I'm more kind of at home in the world of formal methods and verification. So I'm really excited about mathematics, actually. And I still think mathematics is the one thing that we don't teach anymore enough. And I work with companies who want to prove that software is trustworthy. It's not just about writing code, but once you've written the code, or even before you write the code, you want to know that the code actually does what it's supposed to do. And this is something which is incredibly difficult to do, especially if you do it later, and especially nowadays that we have a lot of security concerns. So I work for companies which are interested in testing and verification. And currently I'm leading projects also related to hardware and the next generation of silicon engineering in this field. How do we actually engineer things the proper way? So if there's anyone here who likes to talk more about this or works for a company that might be interested in that, feel free to talk to me as well. I'm always excited to have talks about this and tell people, how we like to do things. And you might, if you're lucky, or if you're lucky, you might see this in the next 5 years being used. But we are quite, I would say, far ahead of what's the current standard, because there's such a big gap between what most companies do and what actually is possible. And so that makes me very excited, because it creates kind of this space of research, space of innovation, that we are, or that our company is working in. Good overview. So I want to show you how you can use this little, this little Pico board to generate a video signal. So those of you who have been to ESG meetings before know that we have talked about signal generation quite a lot. And we have kind of investigated different kinds of signals, UARTs, signals, I2C. We had a whole social about I2C. We had people coming along to show us really how the stuff looks in the real world. Not as pretty as on a function, like not as pretty as we have in a graph. But we never looked at something very complex, really. And I would say VGA is very complex. But what makes it more difficult is that the signal has a very high rate, high frequency in which you need to provide the data. So it's not like you're blinking an LED, which goes half a second on and off. You really need to, push out your data very fast. Otherwise, your screen is going to flicker and you're not going to see anything. So that makes the difference here. So I hope you learned something about VGA in general. So I want to teach you something about the nature of these signals if you haven't seen it. I want to demonstrate a library I started to implement. Now, this library is not yet in a very good state. And I mean, it was when I was learning about the Pico myself, I always set myself little challenges, and that was one of them. And at some point, I needed to do something else, so I couldn't finish it. But I mean, I will upload it, and if someone of you likes to take a step at it and maybe fill in the gaps, that would be really cool. I wouldn't go through all of the code, because the code is a bit not convoluted, but it's not easy to understand some of it. And it's not really the idea to show you the code. But you will find this on the GitHub page that we have in ESG. So let's have a quick look. So this is what a VGA connector is. And I mean, nowadays you don't have VGA anymore. You have, HDMI or other standards. You can even use, other more modern standards for that now. But originally, this was, when I was a student, what was most commonly used. So it's an analog signal, and that means that you have 3 wires here, red, green, and blue. Because every color can be broken down into these 3 parts. And these are analog signals, so they're voltages within a certain range that you're going to send in here. So you need to send these voltages as the beam traverses the screen. So you can imagine you have a beam that goes from left to right and from top to bottom. And as that happens, you're going to change the voltages to actually produce an output of an image. Now, you see there's a bit more happening here. You have these V-sync and H-sync signals on the bottom. And the purpose of these is really you need to know traditionally how CRTs worked. So you have the beam that goes across the screen, but when it reaches the end, it needs to have some sort of impulse to say you need to retract to the start of the screen. Or when you reach the bottom, you need to retract to the top of the screen. And these V and H sync signals were kind of traditionally sort of tied to that kind of logic. So they need to be there in order that you tell the beam, now you're going to go back from left to the right, and now you're going to go back from the bottom to the top. And I will show you a bit more how these signals look, but in effect, it's all of this. So you have the 3 colors, you have the H sync and V sync, and you have a ground. There's no clock. So it's not a synchronous signal. So the only way to synchronize is with these H and V sync signals. So let's go to the next slide. So just in a very brief nutshell, how does the signal look like? So we have the active area of the screen. And imagine in time that we are kind of traversing from here, from the left to the right, and then we go to the next line. And every time you're reaching the end of this, you're reaching something which is called a vertical or horizontal blank. And within the blanking period, you're not displaying any color. You're just, this is the time that you're giving to your screen to retrace the beam to the start. And to make this possible, you need to send an H-sync signal. So every time you're here, you're switching off all the colors, and you're sending this H-sync signal, and that tells it, oh, you have to go back to the start. And you're doing exactly the same when you go down to the bottom. So once you're reaching this horizontal, vertical, no, sorry, this is the vertical blank, you're gonna send this V-sync signal. And I was actually giving a talk some time ago about the Atari, when you know, writing games on the Atari 1600. And the funny thing is that you even in your code needed to generate this V-sync signal. So the Atari didn't have like a video logic that would do all of this for you, and it didn't have a frame buffer. So you needed to basically generate this all dynamically. And it's the same with the Pico, because you don't have a graphics chip on here. You have just the RP2040 processor. That's all you have. So you need to see, how do I generate these 5 signals, the 3 colors, and the V-sync and H-sync. And if you can do this, you're done. You might even get a image out of it. So what's interesting here to note is the actual frequency in which things happen. So a pixel clock, and this is the clock just to display 1 pixel, is about 25 megahertz. That you have 25 million pixels you need to generate per second. Now the Pico runs at a frequency of 133 megahertz, which is about five times as much as a pixel clock, which basically means that you have 5 CPU clocks to churn out 1 pixel. And that's very little. I mean, some CPUs take more than 1 clock to execute an instruction. And depending on the logic behind generating these screens, you might be really pushed to just use the CPU for that. And when David was talking about bit banging, what it really means is that you cannot just use the CPU. The CPU is not fast enough to keep up with that high sort of frequency. And there are some interesting, blogs where they say, well, you can even use an Arduino to do this. And there's a guy, I think called Linus Atkinson, I think, who kind of shows how to do this thing. But the images don't look nice. They are very distorted, very low resolution. But I mean, it might be possible if you do a bit of trickery. But just to say that this is a comparably high frequency for a microcontroller. It's not a high frequency for an FPGA. It's not a high frequency maybe for some high-end systems, but for a $4 microcontroller is a high frequency, I think, to deal with. So this table gives you a bit of an overview where you can see different pixel clocks. And the higher the resolution gets, so when you go to higher resolutions, you see that the pixel clock gets also higher, which means you have to produce more pixel in a second. So from 25 for 640 times 480, if you go to 1,000 times 800 or 768, you're already almost at 100 megahertz pixel clock. And for each of these resolutions, it gives you the exact timing of the sync pulses. So as you can see here, if you go back to just go back to here, this signal needs to be very precise. If it's not precise, you're not going to get the right resolution. And your video hardware is not going to latch onto the signal and give you the right resolution. So the timing is absolutely essential here. And these are basically the standard timings that you have to use. This is basically how it looks in a linear fashion. So if you just have the signals written out, so you have basically your color clock here, you have your sync signal before and after you finished your line, or one horizontal line. You have another sync signal. So this will be for one line. This will be for the whole screen. So here we're kind of zooming into one line. And these are all the different lines. And we finished all the different lines. You're done. And you're doing the same thing again. You're going back to the start of the screen. And these are precise numbers. So you need to kind of be as precise as possible to generate these signals. So what we're going to do, we're going to use the PO, which is this programmable I/O chips. So we're going to generate the H-sync, V-sync, and color signals using the POs. And if you remember from David's talk, the POs have a number of independent state machines. So it's not just one processor, it's I think 4 or 8 of them, which you can all use independently. And then you have 2 blocks of them as well. So we're only going to need 2 of them. We're going to use one to generate the H string and V string, and we use the second one for the color signal. And we will need about 12 instructions of the PO, because also the PO has a very limited instruction space. It only has, I think, 32 or 36 instructions that it can actually encode in its memory. So think about a processor which is very limited, and on top of that only it can have these few instructions. We need a few interrupts. So we have three interrupts, and we will control this whole thing in terms of DMA, but I'm going to show this a bit later. So the PO is really the key to doing that. But I said before that VGA is analog. So does the Pico actually have digital to analog converters? And the question is, it doesn't. So we cannot use the Pico just on its own. And this is why I'm using this base here. So this is the one that David already showed in the talk. And when you look at the left side of the base, what you have here is a resistor ladder. So you can very easily implement a digital to analog converter by a set of resistors. So I'm using this to convert my signal to analog. And there's 4 bits for each color. 4 bits for each color gives you 16 possible colors per color value. Or overall, it gives you something like 12 bits of resolution, which is about 1024 colors, I think. So this is basically all we need in terms of hardware to produce this. And I think I bought this board some time ago. It's quite cool because it also got some other features. It has an SD slot. It has even a converter here if you want to produce sound. So there's even a secondary DAC or DAC, which is another converter to produce audio. So this board is quite useful if you're comparing just to the Pico alone. So this table, we've already seen it. And this is a table that David showed actually, but he was skimming a bit over it because, I mean, these instructions are a bit weird. And if you look at the documentation of them, sometimes they do kind of different things at the same time, and they are not, I would say, you need to get used to this kind of, language. So we have a jump instruction, which is very familiar from assembly. Those of you who have ever written assembly code, every assembly language has a jump instruction. It basically means go to a different address. It's like a go-to, which you don't have in Java, I suppose. You do have it in C, I guess. There's even a paper about it, go-to considered harmful. So we have a wait instruction, which can delay. And this is very important when you're writing these PO programs because they need to be timing precise. And sometimes you just want to delay execution for a number of cycles because you need to do something else. These in and out using something called a shift register. And I don't have this here on the slide yet, but each PO has a shift register, which is basically a register which you can shift data in and out of it. And this basically allows you to say, well, using that shift register to shift a certain number of bits from that registers into the GPIO pins. So this is how we churn out data with the out, and this is how we read in data. So the PO itself, the main thing that it has as a working horse is a shift register. And that's all, a single register. The push and pull are interesting because they are connected to the FIFOs. So the PO is connected on the software side to FIFO buffers, which feed the data into the PO. So these FIFO buffers basically are where the data comes from. And I mean, if you look at the architecture of hardware systems where timing matters, you always have a part which is critical, and then you have a part where you don't know exactly what the timing is. You just need to make sure you're producing data in the right kind of rate, but it's not going to arrive exactly at the same time. And that's the case when you have a CPU, for instance, because the system is very difficult to predict if there's other concurrent things happening. So your FIFOs are kind of in the middle of it. You're putting data into the FIFOs, and as long as you keep them filled, let the POs take the data out at their own pace and the pace that they need to. So these push and pull take the data out of the FIFOs at exactly the right pace that they need to, and filling the FIFOs is not the PO's job. It's the rest of the system that basically does that. So just to give you a simple kind of impression of this, and I hope that doesn't scare anyone, it's a simple program which generates the colors. So at the beginning, you're setting all the colors, so this move pins null is a typical assembly instruction. So the destination are your output pins, and the input is just zeros. So you're making all of these voltages on your colors 0, essentially. You're pushing out a 0, so this is the vertical blank where you don't display a screen. Then you're pulling basically your pixel data. So this pull basically pulls your pixel data. And the issue is you don't know yet, and it pulls it from your FIFOs, so basically. The issue is you don't know when you want to start to generate this, the pixel output. And here you're waiting until the beam reaches the right position. So we have a synchronization mechanism that then says, well, we need to wait until we actually finish the horizontal blank. And at that point, you're going to start then to output your color data for each of the pixels. So this is basically waiting for an interrupt. So we need to use interrupts here to do that. And once this interrupt is fired, now you're reaching this visible area of the screen. And now you're going to loop around, just reading, outputting 16 bits to the pins. As I said, 16 bits is for each color. You've got 4 bits. Well, I'm not sure why it's 16. I think 2 of them are not used. But I think for simplicity, you're pushing out 16 because the resolution is 32 bits. And if there's still more data, you're going to loop around. Eventually, there won't be any more data, and that means you've generated the whole scan line, and then you start again at the start. So as you can see, it's a very simple language, but at the same time, it's useful for what we're trying to do. And if you ever want to generate signals with a Pico, you might study a little bit more what this language can do. And it has a few interesting variations of these commands. So now we've seen the color, but the one thing is who's going to generate that interrupt? Who's going to tell us when we're going to start generating the color? So we're assuming that our PO is clocked and it's working at the same speed as a pixel clock. So we have a second PO state machine which generates this interrupt. And here it gets really complicated. And so let's start from the beginning. So our code starts here, and we have data inside the FIFO. And the data we have inside this FIFO is data which tells us 2 things. First of all, what should we output to the H-sync and V-sync? So this is here we output the H-sync and V-sync. So we take 2 bits of the 32 bits into the FIFO and output it here to the H and V sync. Now here we are fetching the duration of that signal into register X. So instead of writing the next 14 bits to the GPIOs, we write it into a local register, which is called a scratch register. So those of you who ever did assembly programming, you always have a few registers that you can use to do that. And now we're having a loop that decrements X a certain number of times until it reaches 0. So these bits basically tell us how long should the signal persist. And the last 16 bits are not interpreted as a signal, but as a command. So we have 16 bits here, which correspond to an instruction. And this is how we know whether to raise the interrupt or not. So we get another 16 bits from the FIFO that could either be a no-op, do nothing, or it could be an interrupt, raise the interrupt. And this gives the driver of the PO the control to actually say, well, do you want to generate an interrupt or not? Because not all of these phases of the signal should generate the interrupt. Only the one where actually the pixel starts to be generated. And this is based on something I call a synclet. And it's a concept of a synclet is basically part of a signal. It's a signal that for a certain part you output a certain value. And this is how a synclet looks like in the FIFOs. So this is what the hardware, or what the software has to generate and send to the PO. So we have, as I said, 2 bits for the output, the GPIOs. We have 14 bits for the actual delay, how long the signal is going to be generated. And then we have this embedded instruction that tells us what should we do when we finished it. Should we just continue, or should we erase and interrupt? And the C code to generate that based on these 4 pieces of information is given below. So when you design something in the hardware side, this is the kind of thing that you're thinking about. You know, I have the POs, I have the DMA. How do I encode all of that in a way that I can churn out a signal which is timing precise and does exactly the things that you want to do? So once you have that in your head, the rest thing falls together. As it is so often with engineering, you just need one good idea, one good approach, you follow that approach, and once you work through it to the end, then everything just falls like a puzzle piece together. And this was basically the key idea, that you want to have this notion of synclet that the POs can process and they generate the signal for you. So how do we generate the synklets? Well, the POs don't care about the synklets, they're just reading them, but someone has to generate them. Question is, surprisingly, not so surprisingly, that we use DMA. So we have DMA channels, which we set up in a way to produce that data and feed the POs. And what's cool about it is the CPU doesn't have to do anything. The CPU is just setting up the DMA channels. And the rest is really just to respond to 2 kind of interrupts. One interrupt when we reach the top of the screen, one interrupt when we have to prepare the first scan line. I think there's a typo there. And this, the funny thing is, this is Back to the Future. In these 70s, when people started to write games for the Atari, they had to also kind of raise the beam. They had to generate, you know, screen data fast enough or exactly at the right time so that the hardware would generate it as the beam crosses the screen. And this is a bit similar because we still have this issue that we need to generate the scan lines. So everything I showed you here is just about, you know, the nature of the signals, how we generate the right synchronizations. But the DMA needs to write something for the pixels. And this is basically where we need still an algorithm. A CPU needs to take care of it, or something needs to take care of it to generate the scan lines. And it has to do that pretty fast. So this is a part I haven't yet written. And if you're interested, I can share the code and you can maybe have a go at it. But how you do this depends on your application. Old video games hardware, they're using playfield and sprite logic. So you would have to, you know, decode a playfield, and you have some sprites, some color lookups, and things like that. You can have a text screen where you just, you know, have an ASCII map. And bear in mind, the Pico doesn't have a lot of memory. It has 250, a bit more than 250 kilobytes of RAM. And the RAM is the only fast memory in this thing. If you go to the ROM, it's going to be slower, unless you can, you know, the code is small enough to fit in its cache. So there's some pesky details here, how you synchronize between the DMA and the POs, how you set up your clocks so that you get as close as possible to the actual pixel clock, because sometimes you have to compromise on your signals. And there's kind of frequency dividers, which we haven't talked about. They're called PLLs. And there's other features which you can use. But I figured out that this was not completely trivial. You need to play around with some values. So I just want to give you a quick demonstration how this might look like. And just see if I can open a shell here. So this is maybe a bit small. Let me see if I can. Yeah, I'm just trying to make this a little bit bigger, the screen, so that you can see it. Yeah, I think that's probably big enough. So a little bit about the architecture of the PO. It uses something called CMake. So CMake is a kind of something that you impose on make. I mean, those who programmed in C probably have used make. And CMake is a kind of fancy make system, which you don't have to worry about so much the low-level details. You just say what components you want to include. So I can go inside my example now. I just go back, and I'm in the build directory, which is cool. So I go into the examples, and there's already a make file here, so I can just type make. And for those that haven't done embedded programming, the issue you always have when you write for an embedded system is that it's a different language you're compiling to than your host system. So my laptop is a Mac which uses M1 Apple Fabric, and everything I compile here using the GCC toolchain or whatever, or Clang, would be compiled locally. But what I installed now is a cross-compilation toolchain. So the code generated here is not running on the Mac, but should be running on the Pico. And you can download these cross-compilation toolchains, which is the ARM toolchain that I'm using for this one, from the web. And now that we compiled it, what we get basically is an image file, which is this VGA test.uf2. And this is what we want to send to the Pico. So to do that, I plug it in. And somebody asked previously about the boot cell button, and I'm going to press it now. So I need to connect first the Pico device. And now I'm going to reset it, but at the same time I'm going to press the boot cell button. And now it should be in a state where it wants to receive an image. So it's exposing itself on the USB port. And actually, if I go into volumes on my Mac, I should see it. I don't see it, so let's try again. Oh, that's a bit strange. Let me try. I'm just going to unplug it and plug it in again and see if that makes a difference. Yeah, I know why, because there's two USB ports on this breakout board, and I used the wrong one. One is just to power, and one is to connect to the Pico. So let's try again. Yes, and what you see now is that the device appears. While device appears, yeah, so I can send to this device now. And I wrote myself a little script to do that. So it's called Pico upload. And I need to give it the file that I'm going to upload to the Pico, which is this UF2 file. So that seems to have worked. And now it should already start executing the code. Now you can see that there's something on the screen. So if you cannot see it, you can maybe have a look. It's a very simple example where I'm just generating a moving gradient on the screen. And you also see there's two lines here. And these lines are markers which the driver generates in order to tell me how much of the scan line I've used. So as I said, I haven't developed this much further, so I just used some very simple ways to generate those scan lines, but they are not yet doing anything in terms of an image. So that is still something that needs to be done. But timing is super important. So this red line tells you how much you've used of the time that you have to generate a scan line. It's double buffered, so you don't need to worry to raise the beam directly, but you need to stay within this side and between the horizontal blank to basically do that. So when you write this code, that's exactly the kind of things you're thinking about. How much time do I have? How fast is the CPU? Can I actually do this in time? And I can show a little bit more of the code. Thanks, David, that's great. I can show you a little bit more of the code of this example. So I don't want to show you really the code of the DMA and all of the implementation of that, because that is a little bit, I wouldn't say convoluted, but difficult to explain in a short time. even though it does have comments and all that stuff. But let me see if I can get the code of this up. And I just see if I can make this a bit bigger. So I just go into settings and change the font maybe to, let's change this to 24, maybe that's big enough. And just make this a bit bigger as well. Yeah, so when you implement a driver, you want to implement an API for it. And you don't want the user to see all the ugly stuff behind it. You want to just see the nice stuff that you can interact with. And this is an attempt to basically do that. And there's a few initialization functions. But the interesting one is really this one, which is called every time you want to generate a scan line. And this is where you have to generate the graphics data. So there's no frame buffer still. You have to generate the graphics data as you go along. And in this case here, you have basically a buffer, which in Java is an array. So in C, we're using this asterisk here to refer to memory locations. So this is a bit like you would think of as an array. And once you have this pointer to this array, you can write to it. And also the function, when it's called back, tells you which scan line it is. And now what you have to do is to write into that scan line array whatever you want to display. And I have a few examples here which do different things. So the one I showed you with a gradient, I can actually show you another one where I write something different. So I comment this in, which just erases the scan line. So what you have here is a loop that goes from x0 to your resolution and just sets zeros to all the elements of the scan line array. And that just erases your scan line. And the next thing I'm going to do here is I comment out this moving gradient that I have here. But instead, I will just set in a kind of value, which is a little bit random. So I will send the scan line, the pixel, which is scan line times j modulus the resolution. And this j, let me just see where that is defined and what that's doing. Yeah, it's a good question. I think it's some kind of global counter that I just added here. It should be defined somewhere and changed somewhere. Yeah, it's basically changed every time you're reaching the end of the frame. So let's see what happens if I do that. I just save it. And just to show you how this works from a compilation perspective, I do a make. So the make is doing the cross compilation. Now I need to put the Pico into a state again where it wants to read my image, which I just do by pressing the button, and I upload it. And the screen went blank because I reset the Pico. It's not responding. And now you see that there's another thing happening on the screen, which is a kind of random dot pattern. So if you want to see that. And you kind of think, why do I using that much of my scan line already? And the reason here is not so much that I'm writing a single byte of data. The reason is that I need to clear the scan line. So I need a certain amount of time to erase all the information from the scan line. And that's basically what your loop does. So you get a very good idea how a piece of code maps down into a time that is consumed. And it's fairly accurate. I mean, this line is a little bit rugged, but it's fairly stable. So I was pretty amazed because most systems are not very deterministic. But here you get a pretty deterministic picture. So I want to finish here, almost finish because we are running out of time. Thanks, David. But my aim with all of this was, let me see if I can find my keynote slides. And I just go back to play this slideshow. To show you a little bit how different features of a chip work together. This is different from the software engineering job most of you do on a day-to-day basis. Most of the time you're dealing with frameworks, you're dealing with libraries. I suspect, I mean, I don't know, I know there's some of you also doing different things than that. And you have to work your way around all of these frameworks and APIs and libraries and tools. Here, you work around the limitations of a concrete piece of hardware, and you're kind of creative how to use it. If I would have a company, I have a very nice question for you. Assume you want to calculate the divisor, the rest of a division by 3, and you don't have multiplication, or you don't have division. How would you do this? And this is a very interesting question because it brings mathematics, engineering, and design together. So think about this, because that would be the question you would ask maybe in an interview like that. So I will have just one thing here. If anyone's interested in that, I wanted to use this to implement a game, a Donkey Kong game, which is already implemented in Mame. So it's a port from the original arcade, but I haven't done it yet, and I didn't have time to continue this. So anyone wants to work on this together, we're very happy to share the code and see if we can do that. So there's a few more issues with that. You need to port the assembler, you need to do the playfield generation, but I think it's possible. So conclusion. So doing this teaches you a lot about hardware engineering. If you don't want to write a hello world program, you set yourself some challenges. You learn usually more than just going through something that people have done. A lot of people, they do like this technical reviews about things, and they are not, I think in my view, not always very useful, because they always look at metrics. They don't think so much about the design and how things are used, because saying, oh, this chip is faster and slower than another chip. So that's not really the point. So if you have a tricky problem, you have to sometimes look deeper. And you can use CircuitPython as well, although with C++, you're usually getting more out of it. So, and it's also not a bad language to learn, I would say. It's maybe not anymore. It's still used a lot, by the way, despite Java. Yeah, so thanks very much. Running a little bit over time. And yeah, also on the YouTube channel, who's still around. So any questions? Yeah, David?
Yeah. So you mentioned that you didn't implement a library of your own. Is that
yeah.
what are you encapsulating in terms of what?
I think, so the library I needed to implement on my own was a sysdig, because most CPUs have an internal counter that counts like cycles. And this is the most accurate way to measure time, or can be the most accurate way to measure time. And the SDK didn't expose that. So it was not a lot of code. It was 50, 100 pages of code. But I mean, it's just to be prepared that you might find some feature of the chip which the SDK hasn't yet implemented. And there is a VGA library for this. So I'm not going to lie to you. This is not original. I mean, even when I started writing this, I saw there was a VGA library, but I just didn't like it very much. And I thought it was a good learning experience. So yeah, there's a lot of libraries that already does this kind of stuff. Cool. Yeah, I mean, if there's no more questions, that's perfectly fine. So just to bear in mind, thank you guys very much. We do have some, I think, some gifts. Now, Juan, I don't know how we're doing for time.
I think we have some time for perhaps dynamics.